we're going to look at how to balance nuclear reactions in this video. Before you can watch this video, though, you need to know about the types of radioactive decay. So you need to go back and look at the types of decay or the types of radiation video before you do this one, because for balancing equations you have to know alpha, beta, and gamma radiation. So let's start with a review. Where are the parts of the atom? Protons and neutrons are in the nucleus. So protons, neutrons. Electrons are in the outside in the electron cloud. So really when we're talking about nuclear reactions and nuclear equations, we don't really care about these electrons. We're really worried about what's going on in that nucleus, so protons and neutrons. So there's two forces that hold together the nucleus, well, two forces in a nucleus. One is electromagnetic and the other is strong nuclear. The electromagnetic forces are the ones that we talked about back in electrostatics. It's the idea that you have positive and positive, because protons are positive, and they are going to repel each other. That's what those blue arrows are showing, electromagnetic forces. Positive charges want to repel, like repel. But we have these strong nuclear forces, which is just forces between the particles, even positive-positive. And these strong nuclear forces are what actually hold together the nucleus of an atom. So which are stronger? Obviously, the strong nuclear forces have to be stronger because they are responsible for holding this nucleus together. So let's go through how we find out which particular atoms are going to be radioactive and which ones aren't. It's all about protons and neutrons. So first, as protons increase, the electromagnetic force increases. This should make sense because the more positives you add in, the more of a repelling force you're going to have. So we have to counteract this repelling force. This is why, as you get larger and larger elements, you'll have more and more neutrons. Initially, there might be equal numbers of neutrons and protons in the nucleus, but whenever you get up to larger atoms, larger elements, you're going to have more neutrons than protons. And it's because you need those neutrons there to try to hold this atom together. Otherwise, you have a radioactive material and it cannot stay together. The increased number of neutrons will increase your strong nuclear force, but it can only do that to a point. Every atom with more than 83 protons is unstable. So that's when you get to that point where it doesn't matter how many neutrons you throw in there, that electromagnetic force of those protons trying to pull apart from each other, you can't counteract that. And when you get there, that's when you have your radioactive materials. So the strong nuclear forces are not strong enough to hold it together anymore, and it starts breaking apart, and that's what we call radioactive decay. So now let's look at the number of protons and neutrons in different elements here. You'll need to know how to look at these symbols and figure out what are protons and what are neutrons and see how those different decays will affect these numbers. So the first thing we're going to do is put in the full symbols for helium, calcium, and sodium. Now, I know that most atomic weights are decimals, but we're just going to assume we're rounding to the nearest whole number because that is going to be the most common isotope. So for helium, helium's symbol is He. It has an atomic number of 2 and an atomic weight of roughly 4. The atomic number tells you the number of protons. So this is atomic number. So our atomic number is 2, so we have 2 protons. The number of neutrons is the weight minus the atomic number. So here our atomic weight is 4, so we do 4 minus 2, which gives us 2 neutrons. So for calcium, our symbol is Ca, And calcium has an atomic number of 20 and an atomic weight of 40. So that means we have 20 protons, because that's our atomic number. And for neutrons, again, 40, which is our weight, minus atomic number, which is our protons, which gives us 20 again. So notice with these smaller elements, our protons and neutrons are equal so far. But sodium is where you first start seeing this difference. So let's look at sodium. Sodium is Na. It has an atomic number of 11 and a rounded atomic weight of 23. So you can automatically see that you're not going to have equal numbers of protons and neutrons. So our number of protons is 11, because that's our atomic number. And our number of neutrons is going to be the weight, which is 23, minus 11. And so we get 12 neutrons. So here, because we are already getting up to a certain number of protons, we have to counteract that force with a number of neutrons. And yes, I know sodium is smaller than calcium, but calcium is actually stable with equal numbers of neutrons. But sodium is showing you that you can't always assume they're going to be equal. And in fact, when you get to larger ones like uranium and plutonium and all those radioactive ones, you're going to have so many more neutrons than you will protons. Alright, so here we go. We're going to balance our nuclear reactions. What we need to do is know our 3 types of decay. So let's write those out so we've got them. We have alpha decay, and alpha decay releases a helium atom, which is an atomic number of 2 and an atomic weight of 4. Beta decay is the release of an electron, but what happens is a beta particle takes a neutron and creates a proton. So for beta, the beta particle releases the proton, changes the neutron to a proton, which means we're losing a proton as a beta particle, but there is no change to the mass or the weight. The weight does not change, but what happens is this beta particle is essentially losing a proton. Gamma, so for gamma radiation, there's no change in the number of protons, and there's no change in the number of, or the weight. So there's no change at all. So here's the easiest way to do this. If you use the idea that alpha is a helium atom, beta will increase the resulting element by 1 proton, which is what this -1 means, and then gamma doesn't have any change. Then all you have to do is just the math. So here, in our first one, we have a weight of 238, and we're going to 234. The difference there, because left and right have to be equal, means we need a weight of 4. For the atomic number, we have 92, and we have 90, which means to make it equal on both sides, we need a 2. Hey, look, it matches up with helium. And so this is alpha decay. For the second one, our beta means that we're not changing our weight, but we are releasing a proton from the beta particle. So 234 plus 0 gives us 234. 90, and we have a -1 here, so 90 has to equal -1 plus some number, means we're going to have a 91 here. 91 minus 1 gives you 90. That's going to be protactinium. So lo and behold, if you notice, this product is this reactant. So what we're doing here is we're actually looking at the first 3 steps of how uranium-238 changes. So let's look at our third one here. We have 234 and we have 234 on this side. That means we have a zero change. We have 91 on the left, we have 92 on the right. So to equal that out, we have to have a -1. That means beta decay. The last one here, you should notice that both sets of numbers are the same, 40, 40, 19, 19, which means there is zero change, so this has to be gamma decay. And the idea is these usually will have a star next to them, and the star means it's higher energy. And so here, this higher energy star is what is released as the gamma radiation, and you're left with a lower energy of the exact same particle.